Hello, welcome to another Advanced Dynamics lecture. Before we get started today, let's remember a few things from your previous dynamics class. You probably remember velocity, displacement, acceleration, and you probably used it to solve problems like this. If we have an airplane and the exhaust coming out the back exerts a force on the back of the airplane in this direction, that you could solve that the airplane will have an acceleration forward, and mass times acceleration has to be equal to that force. So I think you've seen things like this and you've solved this problem. This is a one-dimensional problem, right? These are vectors, but everything's just moving in one dimension. You probably also solved some that are a little trickier like this. Let's suppose the airplane is just moving at constant speed, but it's diving, right? And it's following an arc with a radius of rho. So what's the acceleration in this case, right? What forces are required to cause this to happen? And if you scratch your heads, hopefully you remember that mass times acceleration is downward. The acceleration is inward towards the center of the circle. And so there must be a force that pushes down on the airplane to cause it to do this. And that force comes from the wings, right? So, and the combination of the wings and the control surfaces on the wings. So just to give you a preview into the things we're going to learn about in this class, let's suppose rather than an airplane, we just were able to pull the engine out of the airplane. And we just had the engine, and the engine has a bunch of blades, fan blades that are spinning, a combustor, and that engine is spinning at really high speed. If we just had the engine go through this maneuver, what we would see is that the forces that we would need the force that we've applied as we worked out above, but we would also need a moment. And it turns out that that moment would be about the negative z, or we'd have to apply a moment this way to keep the tip of the engine from coming out of the page. This would want to come out of the page, and the end of the engine would want to come into the page if we didn't do that. So to make the engine go through this maneuver, we'd have to apply a moment in negative z. And so at first glance, this looks nothing like 202, right? I mean, there's no acceleration that we can see in the z-axis that should cause this moment about the z-axis. And so we're going to need to go to math and pay some careful attention to some of the equations that you learned about in 202 and derive them more carefully for this three-dimensional case. By the way, if this is something that pilots have experienced, and even if you've seen footage of old World War II planes like the P-51 Mustang with a big heavy propeller, they have an engine with a lot of inertia right on the front. And you might see that if you've seen movies, that when the plane goes into a dive, that they'll actually roll. And part of that is to give that z-axis moment that they might need. I think the pilots who flew these apparently knew about this, and they could feel that they needed to use some rudder or some other way to give that z-axis moment if they wanted to go into a sharp dive. So we'll talk more about things like that later. So let's dive right into the math, and as I said, we'll be more careful and derive these things with a little more care. So a basic concept, if we have a point P up here that we're interested in, we can draw a position vector from the origin. We'll also sometimes use the notation RP is seen from O. So the O means that's where we started and the P is where we're going to. So anyway, there's a position vector to point P. And let's say point P is moving along this path, so sometime later it might end up over here at P prime. And So we can use the rules of vectors to say that if our initial position vector is r, sometime later that's r plus delta r, and so delta r is the change in that position vector. And what you can see will happen is if we let time get smaller and smaller, we let delta r get smaller and smaller, then this vector will come closer and closer to the one that we have, to the initial r vector. And eventually we can see that it becomes tangent to the curve. And that gives us the velocity. The velocity is defined as this change in position divided by a change in time. And notice we're being careful to point out that this one's a vector and this one's a scalar. Oops. So that velocity is tangent to the curve because of this property here, that as delta t goes to 0, that this will become closer and closer to r, and v becomes a vector perpendicular to the curve. So in the limit of delta t approaching 0, this becomes the derivative of r with respect to t. So, okay, so that's a position vector, and that's velocity. And this has just an illustration of the same thing, that rigorously v is the limit as t approaches 0 of delta r dt, or dr dt, delta r over delta t. And so we'll write that in this class either as dr dt or sometimes as just r dot. All right, so that's velocity, and we could do the same thing with acceleration. We don't have as good of an insight maybe for acceleration. But if we were to plot velocity path, and we were to look at v and v plus delta v, we could do the same thing to say that acceleration has to be tangent to a velocity curve. We usually can't see a velocity curve the way we can see a road, that a position curve, a road that a car follows. So this doesn't end up being as useful, but it is still definitely true that the acceleration is the second derivative now of position, or the derivative of velocity with time. All right, so that all seems pretty straightforward. And so in general, everything is summarized here. So we have a position vector, we have a velocity vector, and the velocity is tangent to the path. It's also contained in a plane that includes r and r plus delta r. So a plane that contains the path will contain that. And in this picture, we've just drawn the acceleration vector in an arbitrary way to say that it's not tangent to the path. It's tangent to a velocity path if we had one, but we don't in general. Before we go on, there's one problem with this picture. Can you use what I have just covered in the last slides to tell me what that is? Why don't you pause the video and think about that for a minute? So there is a problem with this picture, and then that the acceleration vector is drawn pointing off in that direction. Is that possible? Well, if a particle was really following a curved path from our airplane example, you might guess that the acceleration should be inward. And you could actually derive that if you were to look at this is velocity, and if this was v plus delta v, then, okay, sorry, let me write that a little neater, v plus delta v. These two vectors, the acceleration would connect to the tip of those vectors. Delta v would be this vector right here. So that tells us that the acceleration at this point should be something that's inward and not outward. The acceleration could never point outward like that. Using the math, we can see, we can find an error in the slides. It's been there for 20 years or however long the person who gave these slides to me did that. Okay, also want to review that displacements, velocities, accelerations, they all obey vector addition. So if we had a second position vector, we have point Q out here, and we have a position vector from P to Q, we could put those tip to tail, and then that defines a new vector, and this would be the vector RQ as seen from 0. And that's just the summation of RP as seen from 0 plus RQ as seen from P. And basically when you do this kind of thing, you just imagine the P's canceling, and so you can check that this is worked out. So we'll use that a lot. So that's an example for displacement. The same is true with velocities. If a particle has velocities in two directions, we have velocity vectors in two directions, we can add them up to get the total velocity of the particle. So all these things obey vector addition. When we get to angles, though, we're going to see that all of this becomes more complicated. So here's an example of an angular displacement. We're rotating this bar, OP, about an angle theta z. So if we turn about the z-axis in that direction, then this line OP will rotate, and it'll maintain the same length, but it'll rotate such that P prime comes into the xy plane, leaves the x-axis and comes into the xy plane. So that would be an angular displacement, and we write that as theta z about the k, because the rotation is about this axis. And by the way, it's a good time to mention, I'll probably mention again, the right-hand rule. If I was to take my right hand and curl the fingers in the direction of the rotation, then my thumb will have to point in the positive z. So this would be a rotation about the positive z-axis. So if I try to make my fingers go the other way, they can't, right? So my hands are useful for that. Okay, so do angular displacements obey vector addition the way displacement and velocity do? Well, we can prove that they don't using this example. Say we have this line OA here, and we want to try to rotate it by 90 degrees in two sequences. One of them is a rotation about the x-axis of 90 degrees, followed by rotation about the z-axis. So that one would take this and put it here, and so we'd have A prime on the z-axis. And then if we rotate about theta z, we're just going to spin this vector about its axis, and nothing happens. It's still in that same place. Just to be more accurate, we'll draw it like that. Okay, but notice if we do these in the opposite direction, if we do the theta z rotation first, that's going to take the vector and put it here, give us A double prime. And then if we do a rotation about x, nothing will happen. We're just spinning the vector about its axis. And so this example shows that these two sequences give very different end results. And so we can't say that we can just add up, say, a vector rotation x plus a vector rotation z, because addition cannot depend on the order of operations. It should be independent of that. All right, we're going to do a lot of rotations in this class, and you're going to need to really develop your ability to see in 3 dimensions and to kind of visualize these rotations. So let's take this example a little farther and talk about how we could do an arbitrary rotation. And here I'll just give you the answer for the sequence 1 rotation. We won't go through that one in detail. Let's go through sequence 2. So let's say we want to do an arbitrary rotation about the z-axis followed by an arbitrary rotation about the x-axis. So the trick that we're going to use is we'll always draw the angle as if it was an angle, say, that's somewhere between 30 and 45 degrees. And we'll work everything out, and we'll see in the end that this will work no matter what angle we use. But it's usually easiest to see things if we draw it. I like about 30 degrees because then a 45 degree can throw you off because it looks like, because it's the same distance from both axes. So let's start with the theta z rotation. So what we need is a view in the xy plane of what's happening. And then we're going to rotate about z, so that's going to be a rotation this way. So now we can imagine then that x is going to come up to a new position and y is going to come up to a new position, and that angle that they've rotated through is theta z, right? So now what we need to do is we need to work out what x prime and y prime are in terms of the old x, y, z. And you can actually work this either way. If we're trying to get into the prime coordinate system, then we'll usually want to do it this way. So now what we would do is we'll write some equations, and we'll say that I, or the unit vector along the x-axis, so there's the x-axis, a unit vector along the x-axis would be here, and it's going to have a length of 1, right? So what would that unit vector be if in terms of the xy axis? Well, if we blew up this picture down there, so there's the x-axis, there's the y-axis, here's our unit vector I prime, and this length is 1, and there's our angle. So anyway, we can work out that it will have a component that will be cosine of theta z times 1, which is the length, right? So we don't really need to worry about that. And that will be the I component. And then it will also have a component in the k direction that's a sine theta, or sorry, in the j direction that's a sine theta z. Right, and it will have nothing in the z direction or in the k direction. So now we have an equation that tells us how we can get I prime if we have I and j components. Does that make sense? Okay, so now we can do the same thing with j prime. J prime, in this case, I like to start with the cosine because it's easier. In this case, we'll go up along this axis and we'll go in that direction. So we're going to start again with a 1 times cosine theta z. This time that's in the j direction. But then notice this time we have to go in the negative x direction. So we have to subtract off a component sine theta z in the I direction. And if we were being complete, we would then say that the k unit vector is still the same, so there's nothing that happens there. So that takes care of our first rotation. But we said we were going to follow that with a rotation around x. So we have to decide, is our next rotation going to be around x, the x-axis here? If we do that, we'd call that a rotation about the space-fixed axis. Or is it going to be around x prime, which has already gone through the first rotation? That's what we call a body-fixed rotation. So it could be either of those. We're going to do the second case here. So we're going to rotate about the... Yeah, we'll go ahead and do that about... We'll do the body-fixed case. The example I did earlier was for a space-fixed case. But in any event, in the body-fixed case, what we need is a picture now that lets us see this same thing looking down the x-axis. So we want to put our eyes and kind of look down this way. So if we do that, we'll have a picture that looks like this. We'll have the y-axis, the z-axis. And so we're looking down in the x, and you can use the right-hand rule to check that x, well, we'll cover that later, x cross y has got to be equal to z. Okay, so now we're going to take and rotate this by an amount theta x. And so that's going to bring us to our third coordinate system, y double prime, z double prime. Okay, and so eventually we're going to get really good at this. We're going to do a lot of these, and so that we can write these matrices really quickly. So I won't belabor the point, but again, putting the j double prime in terms of the axes there, this time we'll have a positive cosine theta x in the j prime direction plus a sine theta x in the k prime, and then the k double prime, that axis will have a cosine of theta x in the k prime minus a sine theta x in the j prime, and then the I-axis is unchanged, and that's our and then that is our rotation. And so if this bar OP had gone through two rotations, so if we said that R was some vector with a length L in that direction, so if this was our position vector and it has some length L, and it goes through both of these rotations, when we get done, R rotated, or R double prime, will be L J double prime. And so we could work out then what that is. That will be a cosine of theta x in the j prime, which up above, that's a cosine of theta z in the j minus a sine theta z, oops, in the I. And then we'll add to that a sine theta x in the k prime, which is equal to k. And so now, nesting those two together, we can now tell you where this vector that started in the xy coordinate system, where is it now after going through these two rotations. And so this would give us the I, j, and k coordinates for some arbitrary new position of that vector. You know, it could go through, say a 90-degree rotation, and then it could go through a 45-degree rotation to be in that plane. Well, actually, that would be a rotation about y, wouldn't it? If the first one was about z, the z-axis, that would actually potentially put the bar there. Let's actually make it a negative one. That would put it there. So let's say we put it in this plane here, and then a rotation around x could bring it down into this plane of 90 degrees. Right? And if we just put in the values for theta x and theta z, positive or negative, we could get those coordinates. And if you want to check that, you could do that, right? The z rotation, if we did minus 45 degrees for theta z, and then we did plus 90 degrees for theta x, we should get something that has those components. All right, so that is a quick introduction to how we do these rotations, how we put one vector into a rotated coordinate system. We're going to do that over and over and over again to be able to analyze problems. So you want to get really strong with that. If any of that didn't make sense, bring your questions to class. I have everything written out here in a little more detail. You can also see the answer. We can check that the one that I got is the correct answer. But these direction cosines are basically the components, right? So when I get done, the j-axis, the new j-axis and the old one are related by this cosine theta x, cosine theta z. And so that becomes what we call the direction cosine. We won't use that terminology a lot, but that's something you might hear in other classes after this one. So, so that's the rotation. All of this can be used to define a rotation in a very rigorous way and to define a rotation transformation matrix. And that will be useful to us. And in the most general case, we'll talk about rotations this way. So let's go back and look at this example and see how this might work as a rotation matrix. So here, for example, we're going from the prime coordinate system into the non-prime. So we could actually write all of that as, if we write I, j, k prime as a vector, then we can use these equations to fill in the rows. And what we're trying to do is to relate that to an old I, j, k vector without the prime. These are, I guess, the vector components. We should maybe have hats on them. Okay, so if we wanted to do that, I prime needs to be cosine theta z plus sine theta z, cosine theta z I, so we'd need a cosine theta z in this location. In the next location, we'd need a sine theta z, and then we need a 0. And so when we do the multiplication, cosine theta I, sine theta j, 0k will give us that equation. And similarly, we can write in the second one, sine theta z, cosine theta z, 0. And this last equation will just be 0, 0, 1. And so that is our rotation matrix. And it has the form that we wanted here. We have the old ijk times a matrix R times the new one. And to get the answers that we did in the example we just saw, we got the I double prime, j double prime, k double prime by applying two rotations. First was the rotation about x, and then was the rotation about z. So if we put those two matrices in like this, for body fixed rotations, we put them in reverse order. So in that case, we applied them like that. If we wanted to do body fixed rotations, we would say that our answer, we do them in the opposite order, Rx, Rz, times the vectors in the original coordinate system. And so the book goes through all of this in a lot of detail. And you'll do a couple problems to review that. In our class, most of the time we'll be working problems where it'll be most practical just to kind of draw these diagrams and to work out the rotations like this, rather than just kind of going to the book and plugging these formulas. And often, or the reason that's often better is if the only thing I need to know is J prime, I can just write that out. I don't need to write out the whole matrix if all I want is J prime. So often it's faster just to do that. And so a lot of the problems we will solve like that. So look at the book. That'll help you get through the homework and bring any questions to class. One little example from my work that I just wanted to mention as we end. I work in structural dynamics, and one thing we're working on is the new space launch system right now that NASA's developing. And I ran into this recently, and I thought of all of you in 542. But, a complex structure like this has all kinds of parts. There's the crew module, there's the launch abort system, there's the booster rockets, the engines, or the booster rocket engines and the main engines. And all of these are built by different people. And so anyway, when you put a computer model together for this whole thing, there end up being like 100 different coordinate systems. And even within each component, right? Like you might have one cylindrical coordinate system at that point, and you might have another one at this point, right? And, inevitably the people who made this one will have the axes pointing one way. And, but the people who make the crawler, they decided to orient the axes totally different. And you think I'm joking, but this happens every single time, right? So like if this was X for them, that might be X for them, right? So anyway, everything has a different coordinate system. So when you get a finite element model or a computer model for this thing, it's basically lots of parts stitched together, and all the different coordinate systems are defined, and the key to that definition is a rotation matrix that's just a set of numbers. And this is a matrix just like the matrix R here. And it basically tells you in some other coordinate system, if I multiply by R, I can get the components in my new coordinate system. So, and I forget which way they define it, which one's the global and which one's the local. But anyway, they do this and define the coordinate systems. And you'll see many, many of these in various kinds of work, and you'll use them to do different things. So this is where those direction cosines kind of come in handy. If we look at this one, we see in this rotation matrix, well, that's the component between I prime and I, and we see there we have a value of 0.19. So there's not a lot of that in there. In contrast, if we look at this one, this says that J prime is approximately equal to -1 times I. So that kind of tells us roughly how that coordinate system is oriented, and we can picture that. So that's an example of how direction cosines might be used. And the computer model carries around all of these hundreds of coordinate systems, and it knows exactly how to put them all together and how to do a visualization of how this thing might be moving or deforming.